to the speaker and to some of you. Good afternoon to some other of you, those who are with me here, and good evening to some others of you who are elsewhere. Today we are very pleased to host at the Diller Quantum Center Quantum Seminar Dr. Yosi Atia. Yosi Atia got his first degree at Tel Aviv University. He did his master at the Technion with Tal Mor, and his PhD with Dorit Aharonov in Jerusalem on Shor algorithm and the time energy uncertainty principle, which I think is a very nice thing to hear about. But today he will tell us about work which he did. He is now at Austin, Texas, together with a postdoc with Scott Aronson, and he will tell us about Schrödinger's cat and quantum necromancy. I want to confess that I had to look up the dictionary what necromancy means, and in Hebrew it is להעלות באוב or דורש אל המתים, and I think probably Yosi will explain it to the rest of us what necromancy is. So before I give the floor to Yosi, I think I would suggest as following: since the number of participants exceeds 30, I suggest that if you have questions that you want to pose them, please send the question by chat to me or to the host, and we will either forward the question to the speaker or open your mic. But if the number, okay, and of course there will be time for asking questions at the end. If the number of participants would fall below 30, then I think it's okay for you to open your mic and ask the questions directly. So Yosi, the floor is yours.
So thank you, Yosi, for the invitation. I'm happy to be in Israel again, at least virtually. This is a joint work with my postdoc advisor, Scott Aronson, and with Lenny Susskind from Stanford. Like the title says, it's about Schrödinger's cat and quantum necromancy, which is, necromancy is the ability to manipulate souls, if you may, revive cats. So I want to start very early in the explaining the measurement problem. So we return to the early 20th century to experiments observing electron diffractions and demonstrating the wave-particle duality. So we have a source here, which sends electrons in various directions, and they diffract. They pass through these two slits and interfere on the screen behind it. At this point, since the source sends since the source sends electrons one by one, most physicists would agree that the electron interferes with itself. It passes through both slits at the same time. And we sort of got used to thinking this way for small particles. But on the other hand, in our everyday life, everything is classical. There are no amplitudes or interferences of objects or people around us. We cannot say things in superposition of two sentences. And it seems that the way we think and communicate is classical. And quantum measurement is really the bridge between these two worlds, between the classical world and the quantum world. It's when a quantum behavior becomes classical. So the measurement device gives us one of many outcomes, which becomes then a classical information that we can share and copy and talk about. Um, so, so in this case, the electron behaves completely quantumly in the experiment, and then when it um, and and then when it reaches the screen, we have only one possible outcome of where he landed, even though we can tell what is the distribution of finding him in each position. So the question is, how can the universe have two rules? A random discontinuous irreversible rule for the measurement process that picks one outcome out of many, and a continuous reversible rule for what happens when you don't look. It's also not something we want from a theory. We want just one rule for everything. And to illustrate how strange things can become, we can think about putting two detectors, detector A and detector B, that are that will click if an electron hits them, if the electron passed through the upper or lower path. And we can think about the way to write it is that if the electron, sorry, the slide is a bit too small. So if the electron went up and the lab was silent, then after a while, the electron hits the detector and detector A clicks. And similarly, this is what happened in the if the electron took the lower path, then detector B will click. But since quantum mechanics is linear, we can talk about superpositions, about adding these two transformations, and we get that if the electron went in superposition of up and down, then now we have a superposition of detector A clicks and detector B clicks. And this is something that is not what we want, because detectors are classical. We don't see in everyday life superposition of detector behaviors. And furthermore, we can also add the experimentalist here to this transformation, because the experimentalist sits in the lab and hears a detector A clicks and do something and writes A in his notebook, for example. And when he hears detector B clicks, he writes B in his notebook, but now the experimentalist himself is in superposition. So the question is, aren't we governed by the same laws of particles we are measuring? How come that we are different? How come we feel classical? And where is the boundary between these worlds? And or in other words, where can we say that a unitarily evolving superposition has been measured and that the measurement has produced a single random outcome? If you want to be more spiritual, in some sense, you can ask, well, do we cause the collapse by being sentient beings? And do you have to have a PhD in physics to cause this collapse? Do you have to understand what the measurement outcome is to cause the collapse? And this leads to a lot of interpretations of the quantum mechanics, and Scott gave a really great interpretation decision tree to help us understand what interpretation suits us best. So I know quantum interpretation of quantum mechanics is a sensitive subject, so I hope I don't offend anyone or oversimplify. The first question you need to ask yourself is whether a quantum mechanic is valid in all scales. So in the case you don't think that's true, you think that there is a boundary at which the world becomes classical, then you probably want to look at collapse theories like Penrose and GRW, where they still believe in the in the interpretation of wave mechanics in the Born law, but they add some dynamics to the Schrodinger's equation, some nonlinear elements or some stochasticity that will, from one hand, keep the quantum behavior in the microscale and add some and make a transition to the classical to the classical behavior in the macroscopical scale. One interesting fact is that if you believe in collapse theories, then you also believe that there is a limit to the size of quantum computers that we can build, because in some stage, in some scale, you cannot add more qubits and keep the quantum behavior. Okay, so say that you do believe in quantum mechanics. Sorry, that you do believe that quantum mechanics is valid on all scale. Then the next question is, what do you expect from physics? What is the output that you expect? So if the only thing you expect is just to say what is the probability distribution of your measurements, you only care about your experience as an observer, then you probably belong to the Copenhagen interpretation and to its modern version of cubism, quantum Bayesianism. So here, the observer who is performing the measurements is somewhat outside of physics, and the theory just explained what he's feeling. There could be another observer that is looking at the first observer in superposition, but the wave function in some sense is subjective. And on the other hand, say that you do want your physics to describe the entire state of the universe, then you need some kind of mechanism. You need some kind of you may need some mathematical ingredient to get one world, to decide why we get one outcome and not the other, and this usually involves some non-local hidden variables, which leads you to the Broglie-Bohm theory, where for example, the path of the electron is deterministic, but we just don't have the information to tell exactly where it goes, because we just don't see something. We can't measure something. The problem with this theory is there a lot of ways that to generate non-local hidden variables, and it's hard to determine which theory here is true. On the other hand, you can say, well, there are many worlds, and we don't really know. We're not able to tell the outcome of measurements, because the outcome of measurements just is determined by which branch of the many worlds we went into. So here you just sort of give up on predicting the outcome of quantum measurement by saying this is something outside of this scope. So a question that you can ask yourself, well, do these interpretations even matter? So are we just arguing here about semantics, or is there something concrete that can separate these theories from one another? And is there a way to tell which one is true? Do they give different predictions? And
Yossi, sorry, is it okay to ask a question?
Yes.
So can you go back 2 slides, please? No, the Copenhagen cubism. Yeah.
Yes.
So if I look at many world and at Copenhagen, and I take Copenhagen could mean many things, right? But if we take it to be that quantum mechanics is valid at all scales, because you went to Copenhagen from there, from answering yes. And then if you have an observer, he will see one of the outcomes and we know the probability, but another observer that will look at the first observer can still claim that the first observer is in a superposition because quantum mechanics is valid at all scales. And therefore, isn't this exactly identical to many world interpretation?
Let me think about that. Well, I guess that in Copenhagen and in Cubism, you cannot ask questions about yourself. You cannot ask questions about what happens if you're in superposition. It's just you're classical. I mean, someone else can look at you and say that you look in superposition, and they talk about the wave function as subjective. So it can be and as something that describe your knowledge of the world. So it's possible that two observers will have different idea of the wave function.
Okay.
Does this?
But there is still finally just one wave function of the universe, and in this respect, it is like if you go from another to the next observer and the next observer, and each observer can see the previous one in a superposition, so then it becomes probably identical to the many worlds, right? For the last observer in the line.
Tal, I would suggest that we will have questions, but let's leave the discussion to after the talk.
Sure.
Okay, thank you. Okay, so so do this interpretation even matter, or are we just talking about semantics? So the experiments that sort of test these theories are Schrödinger's cat and Wigner's friend. So, like you know, the Schrödinger's cat experiments, we have a cat sitting in a box, and we have some decaying radioactive element, which probability half will emit a particle, and a probability half will not. So the particle then will start, if it is emitted, it will start some kind of reaction which poisons the cat. So after 1 hour, the state of the cat is also with superposition of being alive and dead. And if you can prepare such an experiment, and hopefully without the poison, and you can verify that this is what you have in your hands, you can start answering questions about microscopic superpositions and whether the observation caused the collapse or not. Another kind of these thought experiments are Wigner's friend, where instead of the cat, we have an experimentalist sitting inside the box, inside the lab. So the experimentalist, who is Wigner's friend, is at the lab making some quantum experiment, and Wigner is standing outside of the lab and looking at his friend and watching him in superposition in the same way we watch the cat in superposition. And here the question is what is the role of the observer in quantum mechanics? How do you feel when you yourself is in superposition? So in today's talk, we'll just try to give some computational complexity point of view to this very known problem. And quantum complexity is the asymptotic number of simple quantum operations required to perform a task. And a side note is a question you can ask yourself is why should physicists even care about complexity theory? Well, complexity theory deals with the hardness of performing different tasks, And it's produced a lot of interesting mostly conjectures about relations between these tasks. And the most known one is the P versus NP question. So in my eyes, these relations are similar to conservation laws in physics that guide our intuition. So by formalizing physical questions in terms of computational complexity, you can sometimes say, well, what you're trying to do is impossible unless P equals NP. Just like today, you can say this is impossible because it violates the second law or violates causality. And another example for complexity in physics is the recent Google's quantum supremacy experiment, when they used the idea from complexity theory to prove that quantum mechanics is still valid in multi-particle systems. And the reason they actually had to do that is that our classical computer cannot simulate multiple particle quantum systems above, I guess, around 20 particles, something like that. So the fact that you cannot simulate the result of the experiment makes it impossible to use the scientific method to verify quantum mechanics, because you cannot predict the result of your experiment and see if it fits the theory. So that's about complexity in physics. Back to the measurement problem. This research was actually initiated by Lenny Susskind, which was working on quantum gravity, and he had different kind of cat states, microscopic superposition. He had superposition of space-time geometries. So I'll explain a little bit about what this is about, but don't worry if you don't understand. It's not really essential for most of the talk. So ADS-CFT is a quantum gravity theory, which assumes that the boundary of anti-de Sitter space of a bulk that we live in, I mean, we live in the Sitter space, and anti-de Sitter space is something else. Anyway, the boundary of space can be regarded as some kind of space-time for conformal field theory. And there is a duality that everything in the bulk inside can be described exactly by the quantum state on the boundary. So there is a mapping one-to-one from a quantum state to the gravity inside the bulk. And Susskind cared about situation where the ADS in the ADS bulk you have different space-time geometries. For example, one with black hole and one without a black hole. And each of these geometries will have a corresponding quantum state that lives on the boundary of the ADS. And by the laws of quantum mechanics, we can find ourselves in superpositions of two different space-time geometries, like the state here. And this leads to all sorts of ideas. One of them is a state dependence of observable, that means that the set of measurements you can or cannot perform depends on the geometry or on the CFT state. This is not something we're used to in quantum mechanics, because measurement is something that is independent of the state you're trying to measure. So just to conclude, the problem that he saw, that if you are in superposition of two very, very different geometries, like one with a black hole and one without the black hole, then each of them will allow you to do inside the bulk different set of measurements. So this is not a state and once you're in superposition of these two geometries, you find yourself in a problem. So that's what he was worried about. And he wondered whether whether computational complexity can provide the ultimate criterion to when two branches of quantum state are separated for good. So he was looking for some kind of collapse that chooses one geometry over the other to avoid this problem altogether. And his conjecture was that detecting coherence between two quantum states is as hard as the relative state complexity. And I'll explain what it means. So detecting coherence is really saying what is the phase between two states. So for example, do we have a black hole plus no black hole, or a black hole minus no black hole? And this task is as hard as the relative state complexity. So it means that if the two branches are very, very different, in the sense that it takes a lot of quantum gates to turn one branch into the other, then this determines how hard it is to detect their phase. I'll say that, maybe I'll try to say that in other words. If the two states are far from each other, then it is hard to tell the phase between them. And if it's hard to tell the phase between them, then there is no effective way to say that they are in superposition and not in a mixture, not in a probabilistic mixture. So if there's no way to see this superposition, then effectively the state has collapsed, just from operational point of view. So in this work, which we will publish one day, we show that Lenny's conjecture is basically true. So this is our main theorem. Given two orthogonal states, alive and dead, suppose that there is a quantum circuit with T gates to distinguish alive plus dead from alive minus dead. Then there's also a quantum circuit with the same order of gates that swaps the alive and dead states, and this is true vice versa. So if someone gives you a circuit that swaps alive and dead, you can also distinguish alive plus dead from alive minus dead. So from here came the name necromancy, because it means that if you somehow manage to prepare a Schrödinger's cat state, and you can verify that you are in this state, you can verify that you're in a alive plus dead state, then our theorem says that you also have the computational power to revive a dead cat. And if we think about Wigner's friend, it means that if Wigner has the ability to see his friend in superposition, then he has some power to change his friend's mind. And that means that Wigner is not such a good friend. So this also generalizes to imperfect distinguishing, so where you cannot distinguish, detect this phase exactly, which is equivalent to imperfect swapping. I'll talk about this a little bit later. And I learned yesterday that Yakir Aronov and Daniel Rohrlich predicted this result in their book from 2005. So how do you prove something like this? So this is basically an exercise in quantum information. So we can define the state psi and phi, which is alive plus dead and alive minus dead. And it's easy to see that alive equals psi plus phi over square root of 2, and dead equals psi minus phi over square root of 2. Now suppose that we have a circuit C that can distinguish psi from phi. So if the circuit gets psi, then it gives a 0 on the first qubit and something else on the rest of the qubits. If he gets phi, then he puts 1 on the first qubit and something else on the rest of the qubits. Then in order to swap between them, we run this circuit. We put alive or dead on this side. And after we implement C, we get to this state. So psi here is turned into 0 and something. Plus is the same plus, and phi become 1 and something else. Now, all we have to do, and if we had a dead state, then this plus will simply be a minus. And now all we have to do is implement a z gate, which invert the sign from plus to minus, and uncompute and run C in reverse. And this will return us from, will turn an alive cut to a dead cut, and a dead cut to a live cut. For the other direction, suppose that we have a unitary U, a circuit that swaps dead and alive states, then we can run this circuit. So say that we put psi as the input to the circuit, U swaps dead and alive, so it doesn't change psi. So it means that this plus state cruises onto the Hadamard and becomes a 0 state. On the other hand, if we have the phi state, then this U will add the minus sign, and so this plus will become a minus, and after the Hadamard gate, we will get a 1. So this is a very simple construction of how to show how these tasks are equivalent in their computational complexity. Just have to notice, so if we have the ability to distinguish dead from alive, that this does not imply that we have the ability to map dead to alive or vice versa. For example, the dead state could be the odd 0 state, and the alive state could be orthogonal to dead. So, and exponentially complex, some very complicated description of amplitude of states that are not the odd 0 state. And it's very easy to determine if you're alive or dead. You just measure in the computational basis. If you get the odd 0 state, then you're in the dead state. If you get something else, then you're in the alive state. But still, turning from dead to alive is very complicated because, again, alive is a very complex state. So we're talking about distinguishing superposition is equal to swap. It's detecting superposition of two state is equivalent to the swap between them. So don't be confused.
Can I ask a question?
Yes.
Can you go to the previous slide, please?
Mm-hmm.
One more. Yes. When you said that suppose that C acting on psi and phi are giving 0 and 1 respectively on the first qubit, but something else on all other qubits, if this something else is not the same in both cases, then it won't really swap them. It will bring you to another state that is some sort of superposition of 0 and 1 probably on the first qubit.
No, it's not true, because if say that I look at this part, if I act with C on 0 and the state here that is depend on 0, sorry, if I act with C on psi, we get 0 and some state that depends on 0. And if we act with C on phi, we get 1 and say state which depend on 1. But if we inverse, we use inverse C, it will take us from this thing to psi, right?
Yes.
And if we invert this part, it will take us to phi. And when I inverted the sign here, I didn't really change these things, right?
Oh, yeah, I understand.
So, okay, cool, good that you asked. So where are we? Okay, so our theorem 2 is basically an imperfect version of theorem 1 with about the same construction. So suppose there is a circuit T with T gates that map dead to alive with amplitude A, which is not necessarily 1, and alive to dead with amplitude B. Then there is also a circuit with about the same complexity that distinguish alive plus dead from alive minus dead with fidelity A plus B of absolute over 2. So fidelity here is the difference between saying plus to the probability to say plus for the alive plus dead and the probability to say plus to the alive minus dead. And what do I want to say? So if you have a weak version of a swap, you also get a weaker version of complexity. And this is also true in the other way around. So there is a special case that I wanted to show here. That suppose that we have a unitary U that takes alive to dead and takes dead to minus alive. Then A plus B absolute equals 0. So in our construction, U provides no real ability to distinguish alive plus dead from alive minus dead. So is there a way, is there a construction that is better than ours, that gives the same, that gives a better fidelity than 0 with about the same complexity as U? So the answer is not necessarily. So these phases actually matter. And here is an example of how to prove something like that. So let's assume that psi is somehow a random state on n qubits. It means that to build it from the odd 0 state will take probably an exponential number of gates. So we look at these states. We have x here, which is 0 on some ancilla qubit times psi plus 1 times the odd 0 state. And our y will be the same composition, only with different phases, I here and minus I there. So it's easy to do this swap with a minus using a single IZ gate. So if you apply IZ, then this area, this part will get an I, move X to Y. And if you apply this on Y, we get minus of what we started with. And on this part, if we apply IZ, we multiply by minus I, which takes this part to this part. But if we multiply by minus I again, we get minus here, minus of what we started. All right, so it takes X to Y and Y to minus X. Now, say that we have a unitary V that is swapping X and Y without these phases. That is A equals B equals 1. In that case, we can apply this V on the state 1 with all zeros, and which is actually equal to X plus IY. This is really simple algebra. Because it's a perfect swap, we get Y plus IX, and Y plus IX equals I times 0 times psi. So any V that can swap X and Y without adding any phase necessarily take the old 0 state and transfer it to the old psi state. So with high probability, this V will have exponential number of gates. So in other words, swap with a minus, the complexity of swap with minus can be exponentially far from the complexity of a swap without a minus. And ideas that are similar to that led us to our tightness result, which is something like the following. So there are a lot of cases where giving a swap with parameters A and B, which is implemented in complexity T, our construction that we gave earlier, these two circuits, are optimal. That is, if we can get a coherence detection with parameters a plus b absolute over 2, but if we try to improve it by even an exponentially small amount, this can increase the complexity by an exponential factor. So in some cases, our construction is the best you can do. And this is true unconditionally without assuming anything like p not equal np. It's just, no, I don't want to go into the proof right now. So I'll try to summarize what we saw. So we had the swap complexity, which is the number of gates required to swap states without the phase. And we have relative state complexity, which is the number of gates required to transfer one state to the other. And clearly, swap complexity is bigger than, I denoted it by S, is bigger than relative state complexity denoted by C, because if you can swap X and Y, you can obviously transfer X to Y. And the last example showed us that there is an exponential separation between swap complexity and relative complexity in some cases. Because we saw an example where A equals 1 and B equals -1, so X went to Y, which is with one gate, which is the relative complexity between them. And on the other hand, if you wanted to swap them, you would need exponential number of gates with high probability. So these quantities are not equivalent. And really swap complexity is what we care about because it correctly captured the hardness of coherence detection. So what happens in quantum gravity? So what are the implications of quantum gravity? So like Lenny wanted, we can treat superposition of space-time as effectively decohered if the two branches are really, really different from each other. And this allow using different operations for each space-time. And this result is unconditional. It means that there is no polynomial time experiment that can observe interference between a state that's exponentially complex and a state that isn't. And once we think that there is no such experiment, they are effectively decohered. And if you join this result with the previous result by Aronson and Susskind on the complexity of the growth of states under a reasonable construction, sorry. If you join this result with the previous result by Aronson and Susskind, you see that there is no polynomial time experiment that can observe interference between an early time and extremely late time in CFT states. They showed in the result that assuming P space is not in PP/poly, something in complexity theory again, then the complexity of CFT states grows linearly, at least before it drops again for a Poincare recurrence. So what is the impact of our work on foundations? Well, to some extent, we just formalized the folklore. So interference between branches stopped being detectable precisely when irreversibility sets in, and when it's no longer feasible to map one branch to another. We used here computational complexity to describe irreversibility. And that's something to notice because there are different ways to describe irreversibility. You can say that some particle interacted with your quantum system and therefore caused it and got out of your hands. And therefore there is no experiment that can tell you that you are in superposition and you're effectively decohered. We didn't use the environment to get decoherence. We used computational complexity. we use questions like how hard it is to measure, to detect coherence, to measure the phase. When we use complexity theory, we like to call everything that is in polynomial time efficient. But when we talk about physics, this is a bit not real, because bringing a cat back to life is just a linear number of operations in the number of atoms. So it's efficient in computational complexity, but obviously not so easy in real life. So you can say, well, maybe the use of computational complexity theory is wrong here, or at least what is easy in terms of computational complexity is wrong. But what is nice about our result is that they're extremely insensitive to the exact criteria of hardness. So if you choose your hardness in a different way, then the tasks are still with the same amount of hardness. So if necromancy is what you call hard, then observing interference is hard. It doesn't depend on what computer scientists considered easy or hard. And yeah, thank you very much. That's what I have to say.
Thank you very much, Yosi. It was fascinating. I think the floor is now open to questions if people want to ask. So other questions, if there are questions from the audience, please unmute yourself and you can ask a question.
Yeah, can I ask a question, please?
Go ahead.
Yeah. So basically, if, I'm trying to make this as simple as possible, you're saying if I can run time backwards, right, then it's, then it's in a superposition and it hasn't collapsed. If I can't do that, if I don't have the resources to do that, it has collapsed. Is that?
No.
Am I oversimplifying it?
No, we're measuring by the amount of, we're not looking at the time, we're looking at how much computational effort you're doing, how many gates you need to do.
So the question is, if I have now more effort, more resources, then, so suppose that I have a certain amount of resources and the thing is collapsed for me, okay? Now if I have more resources, can I now consider it not collapsed?
Yes.
Is that's yes. What I want to clarify. So I can always, the question is, can I always think of some situation where if I have as much resources as I want, I will always be in a superposition and I can always ignore the collapse. My only limit is my resources.
Yes, I think so. I think that's correct.
Okay, thank you.
Can I add something?
Go ahead, Tal.
So, Yosi, can you go back now after we went through the entire lecture to the same, what you call Scott 3?
Yes. Yes.
Okay, so correct me if I'm wrong. So if now I need to judge when I look at this interpretation decision tree, what you're saying, which I also agree it is kind of a folklore that it could be connected to computational complexity, but you and Scott and Lenny succeeded to make the folklore much more mathematical, which is really great. So is it a new type of collapse theory, actually? Because I actually disagree with what I asked and you answered, because if you never have exponential resources, you can only have polynomial resources, then it is not anymore a matter of Copenhagen cubism or Wigner-Friend seeing Wigner in a superposition, because it stops there. It stops the moment there is exponential complexity. So it is kind of a collapse theory, even if there is a wave function of the world. from every practical point of view, you cannot go beyond the collapse theory. You don't have the resources anymore. You need exponential ones, which are unfeasible.
Yes, I
This
guess.
was not a question. This was an observation, right?
No, the question is how to connect it to Scott's interpretation decision tree. And I also added my view of the reply to what Shai asked.
So about whether this is a new kind of collapse theory, I guess you can say something like that. I mean, if you assume that there is a limit, the quantum Church-Turing thesis is what we have. So everything we can do in the world is polynomial time is equivalent to a polynomial time quantum computer. Then I guess yes. I guess this tells you some kind of a limit, also about how complex, what piece of the quantum world you can see, and when things become classical to you just because you simply cannot see them.
And it goes beyond Church-Turing, because the separation is between exponential time and polynomial time. So even if BQP equal QMA, for example, or like P equal NP, but the quantum version, still your separation is between polynomial time and exponential time, which is always true.
I guess so. I mean, we didn't really set the limit exactly. We said, well, if you consider polynomial time to be your limit, then this is where effectively you cannot see superpositions anymore, and you see somewhat of a classical world. But I guess we didn't do it exactly. We didn't say exactly where the line is, because it can be much simpler. You can say, well, I cannot revive cats, which is a linear time. So this is my limit, and not polynomial to exponential. So I guess we left that part open.
So are there other questions from the audience? If not, I would like to ask one question. In the computations that you showed us, there was a symmetry between being alive and dead. Everything was dead cat, and the argument could run. But killing a cat is easy, and reviving it is difficult. So where do I see this in the kind of computation that you showed us? How do I see when something becomes what you called irreversible?
It's a good question. I didn't think about that. Because I guess you can say that the relative complexity of alive and dead is the number of operations you need to move from one to another. Yeah, I don't have an answer.
I think actually there may be in one of your transparencies when you showed, perhaps it's related to the superposition between a state that was easy to make and a state that was very difficult to make. Is this where I should think? You showed us such a superposition and drew some conclusion from this. You know what I have in mind?
Is it this slide?
No, there was an equation. An equation where there were lots of zeros and then a state that required exponential many resources, right? So perhaps, is this correct that I should identify, say, the psi with a live cat and the zero with the dead cat? So one of them is easy and the other one is
no, I think here, yeah, I guess here you can say, yeah, I guess you can say that psi is an alive cat and all zero is the dead cat. I'm not sure. I have to think about it. I just don't see an answer right now.
Yosi, Yosi, I think the answer to this will require adding temperature into the picture, because the dead cat can look exactly the same whether you are at room temperature or at millikelvin temperature, but the alive cat will be very different in millikelvin versus room temperature. So I think you need to have temperature in the picture in order to see that the dead cat is really a much simpler state.
I see, Tal, you want to cook the cat in addition, right?
On the contrary, on the contrary.
If I may add some idea. Hi, this is Moshe Goldstein from University. So I guess to go from a complicated state to a simple state in the analog of killing a cat, I think is suppose you just measure all the qubits in computational basis, and then you get zeros and ones, and then flip those that are ones. Then it's easy to get to the state of everything zero, right? It's easy to initialize. But of course, to do it the other way is hard. But I guess it's relying on being able to do something irreversible, like a measurement.
Mm-hmm. Yeah.
And somehow you are only using elements which are reversible, which are unitaries.
Yes, that's a good answer. Thank you.
Okay. If there are no more questions, I want to thank again Yosi Atia for a fascinating talk and for a new perspective on Schrödinger cat. Thank you very much, and have a good breakfast now.
Thank you. Goodbye.
Okay, thank you, everybody.
Thank you. Bye-bye, Yosi and Yosi.
Okay,
Bye-bye.
bye. So since Daniel is here, can you tell us what was in your book with Yakir? To what extent you predicted this?
Yeah.
Did you talk about complexity, or it was some other
No,
notion?
it was not a language of complexity. We never got into complexity, but I think it's very natural for complexity to be here, because if we're going to try something really fantastic, like putting a cat in a superposition of states, then we obviously need very, very special tools to do that. I'd like to, however, share my perspective of what all this work means. What it meant for me is that we should be very careful about how we use the phrase "in principle," because one can easily say, in principle, we can make a superposition of two cats, a live cat and a dead cat. Or sorry, one cat, but the live state and the dead state. So you can have live plus dead. But if you have an operator like that, which gives you a measurement of live plus dead, it has other eigenstates as well. It might have live plus dead as an orthogonal eigenstate. And then you get into the possibility of transforming a state live plus dead into live minus dead. And then when you add those, you can change a dead cat into a live cat. And I don't think that we should be saying that in principle, we can change a dead cat into a live cat. I don't think that in principle retains its meaning. Certainly not when you take the next step, which is perhaps not much further, that you can take a dead human being and turn him into a live, him or her into a live human being.
So what is the thing you are objecting to? I mean,
I'm objecting to say,
it's not clear what one means by in principle, right?
when you say in principle, you're in some way fooling yourself and maybe other people as well. Because we cannot say in principle we cannot say in principle we know quantum mechanics so well that we can turn a dead human being into a live human being. No, that's nonsense. We don't have that. So don't use the word in principle there. We've already wandered beyond some computational range where this.
But if I use the word in principle to mean that I have unbounded resources, you still object to that? It's not clear what one means by in principle, right?
It does not clear what you mean by unbounded resources either. It's exactly the same situation.
I don't know. It sounds to me like we are getting into these standard issues in logic of talking about sets that that are ill-defined, you know, like
Well, okay, so
notions that are ill-defined.
if in principle doesn't mean anything well-defined, then don't use this expression, please. I mean,
Okay, I see your point. Okay.
Well, maybe we can say that in theory and practice are the same, but in practice they are different.
good to see you.
Okay. Very good. Good to see you, Daniel.
Yeah, good to see you, Daniel.
Thank you.
Okay,
You well.
good. So, thanks everybody.
יישר כוחכם.
יישר כוח, כן.
יישר כוח.
טוב,
Bye.
אז להתראות כולם.
How do we get out of here? Leave.